So, in the next topic, we'll be talking about finding the algebraic roots of polynomials by using Horner's method. Okay? So, in this method, we will have a mixture of Newton's method in this because Horner's method can be a pattern to Newton's method. So in solving for algebraic roots of polynomials, say we have a polynomial of p of x is equal to say a plus bx plus cx squared plus dx cubed. This is an example of a polynomial. Okay? So in algebra, we have different types of solutions. In solving for polynomials, we can use the quadratic equation if the polynomial is in quadratic form. We can use a quartic equation. Okay, a quartic equation. Or we have in other books. Oh, sorry, before quartic equation, we have we have cubic first before quartic. So cubic equation. So we can use this. And quartic, wherein a polynomial is in a fourth degree. And quintic is not solvable anymore by algebraic solution. And this was proved by the Abel-Ruffini theorem that there's no such thing as a quintic equation, or there's no algebraic solution for a quintic equation. So the Abel-Ruffini theorem proved that. So other method that we use is rational root theorem. Okay, but we're not gonna dig in with the rational root theorem or the quadratic equation or quadratic formula because this is in algebra. But we're gonna dig deep in how Horner's method is used to solve algebraic roots of polynomials. So these steps are simple in using Horner's method because we know that in Newton's method, we know that x of n plus 1 is just x sub n minus the f of x sub n all over f prime of x sub n. In the case of Horner's method, we just change the value, or we change the terms in Newton's method. It just becomes x of n plus 1 is equal to x sub n, and the function just changes. It becomes the polynomial given to us. So a function is a function, but a polynomial is different from a function. So you just get its derivative. So when finding for the derivative, of a polynomial, okay, if we recall in our differential calculus, we can use power rule. Okay, so take note, you use power rule in finding the derivative of a polynomial. And now we can evaluate for p of x and p prime of x using Horner's method. Okay, using Horner's method. And for some cases in algebra, if there are too many roots, say for example, we have a 7-degree polynomial, therefore it has around 7 roots. If we don't know where to start, take note that our starting point here, we can set x is 0. Because sometimes the roots of a polynomial is a mixture of positive and negative numbers. Of positive and negative numbers. So in this method, if we don't know how to start with our iteration, we can set the starting point as x is equal to 0. Okay? So after several iterations, so we can round up. Okay, so we can round off the answer if we notice na papalapit na siya dun sa magiging root natin. Okay, so let's give an example of a polynomial. So p of x is equal to, say we are given this polynomial x to the fifth minus 8x to the fourth minus 72x cubed plus 382x squared plus 72x minus 2310. So by using the power rule in differential calculus, we can get the derivative of this, which is 5x to the fourth minus 32x cubed minus 216 x squared plus 764 x plus 72. So that is the differentiated polynomial. So we just substitute this with our equation x sub n plus 1 is equal to x sub n minus p of x n over p prime of x. Okay, so we set our starting point to x is equal to 0. So we have our x sub 1 is 0. So we have our x sub 2 is equal to 0 minus, so we have 2, 3, 10. We have 2, 3, 10 over 7 to 7. And that lead us to the answer. 3.17, 74, 41, 54. And after doing so many iterations, we will conclude to the answer that, so after doing this step several times, we can arrive to the 7th iteration wherein the value of x is now 1.9999, and we can round that off so we can find the root, which is 2. Okay, so that is how the Horner's method works in solving for the roots of polynomials. So after finding for one of the roots, we can now deflate our original equation. When you say deflate, we can now divide the equation by this root by using synthetic division because it is much easier. Okay, but I'm not gonna dig deep into using synthetic division. Okay, I'll just show the deflated equation. So now that the polynomial becomes x to the fourth, so it becomes x to the fourth minus 6x cubed minus 84x squared plus 214x plus 1155. And then restart Horner's method. Okay, we use again Horner's method. We solve for another root. which is negative 7. And then we deflate it again, deflate the equation, so it becomes p of x is equal to, so we deflate the equation by using synthetic division, and we divide it by this root. So it becomes x cubed minus 13x squared plus 7x plus 165. So again, we restart the Horner's method until it finds its root, which is negative 3. Again, we deflate this by dividing this equation by its root so that we can arrive to a new polynomial, which is x squared minus 16x plus 55. Now, we restart Horner's method again until we find the root, which is 5. And now lastly, we deflate it again until we get a polynomial which is equal to x minus 11. You don't need to use Horner's method because it is obvious that one of the roots is equal to 11. So now the roots of your polynomial are this, and this. So we just write them down. Your roots are 2, negative 7, negative 3, 5, and 11. So this is how you find the roots of a polynomial using Horner's method.